Hey, welcome back. Today I want to talk about E equals mc². From my childhood in the 1960s and 70s, E equals mc² was just all over the place. It was part of popular culture, but no one was able to explain what it meant. If you're curious, stick around. I will try to walk you through the steps of what this equation is telling us. E is energy. It's an amount of energy. M is mass. So mass is a measure of matter. C is the speed of light. The 2 means the c is squared, so we have the square of the speed of light, and that is already a mind-bending concept. This equation is definitely not a recipe for making nuclear weapons. It is not a formula for turning matter into energy. It's not even saying that matter can be converted to energy. What it's really telling us is that matter has mass. Mass is a property of any piece of matter, and mass is a form of energy. So you don't have to convert matter to energy. Matter already is a form of energy. I have 2 disco balls. So let's pretend that these are spheres, and let's just pretend that this one is exactly twice the size of this one. So twice the diameter, 4 times the surface area. Imagine that you're out in space with a lamp, and you switch it on and switch it off immediately. What you've done is project light. It's going to go outward in all directions, just like light from a star. And that pulse of light is going to take the shape of a hollow sphere. And it's expanding. How fast is it expanding? Well, light moves at a specific speed, and that speed has a name. We call it the speed of light. So it's expanding at the speed of light. So after one short interval of time, that sphere of light will be this size, and after a second interval of time, it'll be this size. In this sphere of light, regardless of what size it is, it's the same amount of energy, and energy in the form of light. But we know that the bigger sphere has 4 times the surface area than the smaller one. So that means the same amount of energy spread out over 4 times the area means that any particular spot on the surface is going to get 1/4 of the amount of light that the same spot on the smaller sphere would get. This one is 4 times the size, so each spot gets 1/4 the amount of energy. That is the essence of the inverse square law. If you're twice as far away, the light is 1/4 as bright. So sometimes it's easier to think of this in terms of cupcakes. So let's say you have a cupcake and you have another cupcake that's twice the scale. The surface area of the larger cupcake is going to be 4 times the size of the smaller cupcake. But if you have to frost the 2 of them with the same amount of frosting, the frosting layer on the bigger one is going to be 1/4 as thick. I used the example of cupcakes and light, but the interesting thing is gravity works the same way as light with the inverse square law. So every object that has mass exerts a force on every other object that has mass, and that force is called gravity. But it's weak enough that we don't really notice it unless you get a really big object like the size of a planet. Then we definitely notice the gravity. We can say the planet is pulling this massive object, this pen. When you let go of it, the force of gravity makes it fall downwards. And downwards is just our everyday expression for the direction that gravity pulls things. But the pen also has mass. It's pulling up on the Earth at the same time. So every object that has mass is exerting gravity, and the force of that gravity obeys the inverse square law. That is, if you're twice as far away, the gravity is 1/4 as strong. So there are different forms of energy. Light is one form, electricity is another familiar form, and the motion of objects is another. And here's a 10-pound dumbbell. It takes energy to move this around. We can measure this in our exercise and figure out how many calories we're burning as we move this massive object. So we can move this with the power of our muscles, but gravity can move a massive object by the power of gravity, which is inherent in all objects made of matter. Gravity can move objects, and moving objects is a form of energy, so mass is inherently energy. Einstein took what was a radical view at the time. He said the speed of light is a fixed constant in the universe, regardless of who is looking at the light. The conclusion that led to is that time and space are relative. There's an amount of energy that corresponds to your amount of mass in an object. You multiply that amount by the speed of light squared. You move a certain number of meters in a second, and that's whatever speed you're going. And in ordinary experience, we sometimes think of miles per hour or kilometers per hour. That's speed in a car. That's our ordinary experience of speed. You can convert miles to meters, you can convert hours to seconds, and you can get meters per second. So c is the way we typically express the speed of light. If you pretend that c is just the number, c in parentheses, meters per second, c squared, that number squared, meters squared divided by seconds squared. So this is the part I want to explain. Pretend that's a meter, then this would be a meter square. A meter square is a unit of area. There is a name for the distance light travels in a second. It's called a light second. You might have heard of a light year as a very long measure of distance. A light second is a much shorter unit of distance. So even though it has second in it, which is a unit of time, light second is a unit of distance. A light second squared is a unit of area. So if the smaller one just happens to have 1 light second squared of area, the larger one has 4 light seconds squared of surface area. So after 1 second, this sphere with a radius of 1 light second. After 2 seconds, you have a larger sphere with a radius of 2 light seconds. And then you will just keep getting larger spheres every second that you proceed. So what c squared, the speed of light squared, is getting at is the fact that when you get to larger and larger spheres of energy propagating through the universe, the surface area increases exponentially in a way that corresponds neatly to c squared. Scientists would tell us that this expansion that I'm talking about is not really what the meters squared per second squared in the formula is talking about. They would say it's just a mathematical way of expressing energy. That meters squared per second squared is just the definition of energy in mathematical terms. But that's so abstract, it is hard to grasp. So that's why I took the time to explain this idea of area and the accelerating expansion of area. So maybe it's just a cosmic coincidence that the squared figure here corresponds to the accelerated increase of surface area as light propagates through space. This is like the kind of thing a child would ask about and say, that's interesting, what does that mean? And scientists are just not curious the way children are. They would say it doesn't mean anything, it is just the mathematics of this. So maybe that meaning will be discerned and explained by someone eventually. So this equation is telling us that matter, by having mass, is already a form of energy, and it's a pretty large amount of energy in each bit of matter. All right, so I hope you learned something. I hope this was interesting for you. That is all for today. Thank you for joining me, and I will see you tomorrow.